Have you ever wondered how ChatGPT works and how it gives accurate answers to your questions? Well, today we're diving deep into a custom implementation of a GPT-like model. We'll explore every aspect of its construction, starting with the overall model architecture and working our way down to the detailed training loop that brings all these components together. Get ready to uncover the fascinating mechanisms behind this powerful language models. Before starting the video, make sure you have PyTorch installed on your PC and some knowledge of Python. If you don't have PyTorch installed, follow these steps. First, search for PyTorch on your browser. Then open the official PyTorch website and scroll down to find the installation guide. Choose your operating system and CUDA 11.8 version. Then copy the command provided below, if you have Conda. Activate your environment and paste the copied command into your command prompt, and then press Enter to execute the command. At a high level, our GPT model generates text by predicting the next token based on the tokens it has seen so far. It consists of an embedding layer to convert tokens and positions into vectors, followed by a series of transformer blocks. Each block has a multi-head self-attention mechanism and a feedforward network, or MLP, with layer normalization and residual connections. Finally, a linear layer maps the output back to the vocabulary space to produce logits for each token. We will start by defining our GPT class, which inherits from nn.module, just like any other PyTorch model. Inside the constructor, we define the key parameters. Dim is the size of each token embedding. Vocab size is the number of tokens in our vocabulary. Context len is the maximum sequence length. NumHeads is how many attention heads we use. NumLayer is how many transformer blocks we stack. And dropout is used to prevent overfitting. We initialize the parent class using super. We store the context length as a class variable to check sequence limits later. This layer converts token indices into dense vectors of size dim. Since transformers don't have built-in order, we add learnable positional embeddings here. This is the dropout layer, used for regularization after the embeddings are added. We create a list of transformer blocks. Each is a layer in the GPT model. Block is defined later, and we stack as many as numLayer specifies. We apply layer norm to stabilize the outputs before generating final predictions. This final linear layer maps the output vectors back to token logits, one logit per vocab token. We tie the weights of the output layer and the embedding layer, a trick to reduce the number of parameters and improve performance. Now we define the forward method, where the input x is a batch of token indices. We extract the batch size b and sequence length t. We check if the sequence is too long and raise an error if it is. We create position indices from 0 to t1 to fetch positional embeddings. We get the token embeddings and add the positional embeddings. We apply dropout after embeddings to reduce overfitting. We pass the input through each transformer block in sequence. After all blocks, we normalize the final output. We apply the final linear layer to get the logits for each token in the vocabulary. Finally, we return the logits for each position in the sequence. Next, we define the block class. This represents a single transformer layer. We take the same hyperparameters and initialize the sublayers. The first layer norm is applied before the attention layer. We define the attention layer. It's causal so that the model only looks at previous tokens. We define another layer norm and the MLP, the feedforward network. In the forward pass, we first normalize, apply attention, and add a residual connection. Then we do the same with the MLP layer. This completes one transformer block. Now let's build the attention mechanism. We ensure that the hidden dimension can be split across the heads. We store the number of heads and embedding size. We use one linear layer to compute all three: query, key, and value vectors. This projects the output of attention back to the model dimension. We create a lower triangular matrix for masking future tokens. This is the causal mask. Dropout is applied to the attention and output to prevent overfitting. We get the batch size, sequence length, and hidden dimension. We pass the input through the linear layer and split it into query, key, and value vectors. We reshape and transpose the tensors, so each head gets its own chunk of the data. We compute scaled dot product attention, Q times K transpose divided by the square root of key dimension. We apply the causal mask so that tokens can't look into the future. We apply softmax to get attention scores and then apply dropout. We multiply attention scores with the values and reshape the result. We apply a final projection and dropout and return the output. We start the feedforward network with a linear layer that expands the dimension 4 times. We use GELU activation, smoother than RayLU and great for language models. Then project the data back to the original dimension. Finally, we add dropout for regularization. In the forward pass, we apply linear, GELU activation, projection, and dropout, simple and powerful. This was the architecture of our custom GPT model. Now let's dive into the training loop where the model actually learns. We define a trainer function that takes in the model, the data loader, number of epochs, and a path to save the snapshot. First, we set the device the model is on, either GPU or CPU, and define the loss function. Here, we're using cross-entropy loss, which is commonly used for classification tasks like language modeling. Then we initialize the AtomW optimizer, which is a variation of Atom optimized for training transformers. The training loop runs over multiple epochs. For each epoch, we set the model to training mode and initialize the running loss and step count. We also create a progress bar using TQDM to track training status live. Then we iterate over each batch in the data loader. Each batch contains tokenized input IDs. We check the sequence length and skip batches longer than 1024 tokens to stay within model limits. For valid batches, we prepare inputs and targets. The inputs are all tokens except the last one, and the targets are all tokens except the first. This offset creates the next token prediction task, which is the core idea behind language modeling. The model processes the input and produces logits, raw predictions for the next token at each position. We reshape both the logits and targets so that the loss can be calculated properly over the entire sequence. Next, we perform the standard backpropagation steps, zero the gradients, compute gradients with loss backward, and then update the weights using optimizer, step. We accumulate the loss across steps to calculate the average loss for the epoch. The loss for each batch is also shown in the progress bar in real time. After each epoch, we optionally save a snapshot of the model's state to disk. This is useful for resuming training or doing checkpointing during longer training runs. Finally, after training is complete, we save the fully retrained model to a file. And that's how this training loop teaches a GPT model to understand and generate language from your dataset. Here's a brief conversation with our custom GPT model, which has been instruction tuned for question answering. So that's how you build a GPT model from scratch using PyTorch. Let's quickly recap. We built the overall GPT architecture. We implemented the transformer block. We created causal self-attention from the ground up. We added a powerful feedforward MLP. We understand how training loop works. If you found this helpful, leave a like, subscribe, and comment below what you'd like to learn next. Thanks for watching this video, and I'll see you in the next video.